All right, so psychrometrics is literally just, I mean, if you want to be fancy, the physical and thermodynamic properties of air, especially as it relates to human comfort, blah, 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 blah. It's about air. It's the science of air. And specifically, what we're going to talk about is just some basic, like again, I'm not, as you've probably noticed, I'm not a big formulas guy for text. It's not, to me, it's not that useful. But we can, so it's not about memorizing numbers as much. But there are some things that you should definitely know about. One of the things that that's important to know about air, first and foremost, is that air is stuff. It's not nothing. Air is made up of stuff, and it takes up space. It has weight, and it takes up space. So it's not the absence. It is something. It's mostly nitrogen, water vapor, oxygen, carbon dioxide. It's a mixture of different things. The one part of that equation that changes significantly in terms of air's makeup is how much water vapor is in it, right? So, and that's the big thing that we obviously are going to talk about here. One thing about air, the weight of air, like even on this slide, it says air weighs 0.75 pounds per cubic foot. So a lot of times I'm going to talk about boxes of air, okay? When we talk about a CFM, what does CFM stand for? A cubic foot per minute, right? Not a cubic meter per minute, because we're from America here. I do kind of, it throws me off when I'm driving and it's like 900 meters. I'm used to like 900 feet. It's a big difference. But it's a box of air, right? So box of air like this, and that's what we're moving around. But that air, when we say it weighs 0.75 pounds, what does that mean? What does it mean that air weighs something? Because, like, do you feel air? Like, how does that work? But again, we're immersed in it, right? So it's pushing on all sides of us. So we don't sense it because of that, right? But again, we know that air is stuff because when I wave my hand around like this, I can feel it. And what am I feeling? I'm feeling the little molecules actually bouncing off my hand. It's really important that we get kind of a grasp on that. So a lot of the times when people just don't understand what's going on with this, they don't get that the makeup of air is not a fixed thing. So even when things like barometric pressure change, which they do, it's not a lot of pressure difference, but that density of air changes. So when we say 0.75, that's not a fixed number. If we go up into the mountains, what happens to the weight of air? It decreases, right? On a per volumetric per volume, the weight changes, right? And so what happens to the density of air when you go up into the mountains? Well, no, lower density, right? Lower density air, okay? Temperature-wise, let's talk about temperature. So what happens when you heat air? Does it become more dense or less dense? When you heat air, it becomes less dense. Why? Because when you heat things, all right, look, I didn't want to do this. I did not want to do this, but you're going to make me do it, okay? It's the thing that I do that embarrasses all my technicians and my children most, but I'm going to have to talk to you about jiggly, okay? So, if I take this chair and I heat this chair, well, let's start with this. Okay, so what is this chair made of? Made of metal, and it's in what state? Solid. It's a solid state, okay? Which means that all of the molecules that make up this chair are in like a crystalline structure. They're all bound together, right? If it was liquid, then they would have some bonds, but they would be able to flow. And if it's vapor, the bonds are broken and they kind of bounce all over the place, move all over the place, right? You got that? That's all that's going on is those bonds between them. So this is solid. Now, if I heat up this chair, what happens to the molecules inside this chair? They jiggle more, right? Because they can't, and they do expand. They do, but they expand, they don't expand a lot because obviously it's in a solid form. It's in that solid structure. Now, if I keep heating it and keep heating it, at some point, what happens? It melts, right? Those bonds break and they start to kind of come apart. If I keep going and keep going, I could actually turn this chair into a vapor, right? But it all comes down to jiggly. When you heat it up, those molecules jiggle. And the more you heat it, the more they jiggle, right? And so when you're taking vapor, air, water vapor, whatever, and you heat it up, what do those molecules do? They bounce around more. And when they bounce around more, what do? They separate, they expand, right? So everything expands to some degree, back to what Fabian said, everything expands to some degree when we heat it. There are some weird exceptions when things become solids. Like, for example, why is it that when water becomes ice, it actually expands? You all know that, right? Why is it that happens? Like, if I take a water bottle and I fill it all the way up to the top and I throw it in the freezer and I let it freeze, it'll like burst the water bottle. Water expands when it freezes. And why is that? It's because if it didn't do that, when ponds freeze, they would freeze from the bottom up and all the fish would die. So of course, they had to make sure when they got together and made water that they didn't want the fish to die. So they designed it that way, so that way it would float to the top and the fish would be able to survive. I tell that joke every time and nobody ever thinks it's funny. So the reason why is because it creates this very crystalline structure that actually has gaps and spaces in it. So as it actually freezes, it actually separates a little bit and creates a much more crystalline structure. And so it becomes less dense and it floats, right? Okay, back to air. So hotter air is less dense, which means that it weighs less per cubic foot. So the weight goes down. All right, here's a fun one. Is wetter air, more humid air, lighter or heavier than dry air? Heavier, right? It's got more moisture in it, right? Air that is more humid is heavier. The answer is no, it does not. More humid air is, in fact, lighter. And it's crazy, okay, because I didn't know this for the longest time. Now here, let's first focus on why we think that, because it's very sensible that you would think that. Because when you walk outside and it's really humid, right? How do you feel? You feel heavy, right? You sweat and it's heavy, and it's just, and when you look at water, you're like, of course water's heavier than air. Don't be ridiculous. Look at it, sitting in that water bottle right there, right? It's heavier than air. Well, yeah, but you're talking about liquid water. You're not talking about water vapor. Water vapor is lighter than air. In fact, if we were to measure the total moisture content near the peak of this room versus near the bottom of this room, you would find that there is a higher moisture content at the roof than there is at the bottom, because water vapor is lighter than dry air.
That actually makes sense because heat rises. Moisture is going to cut off.
There's a proportionality there, yeah. Here's why, though, the exact reason why it makes sense, and this is a real scientific blibbity-blue, but H2O, right, hydrogen and oxygen, that's what water's made of. It's made of 2 hydrogens and 1 oxygen. So if you look at that molecule, hydrogen is the lightest molecule there is, right? It's a single atom, single hydrogen, very, very small. And then you look at oxygen, so when you talk about the actual atomic weight, it's a 1 and a 1 and a 16. That's 18. Air is made up of mostly nitrogen, which is N2, which is 2 14s, which is 28, and O2, which is 2 16s, which is 32, right? So when you look at it, obviously, it's quite evident why H2O is actually significantly lighter than a combination of N2 and O2. Now, air is also made up of other stuff too, but all in, water vapor is significantly lighter than air. So as a mixture in air, and it does mix, so it's all mixed together in this homogeneous mixture, it is lighter, and the water vapor does make its way up, which again, we know this. Have you ever been outside and looked at clouds before? How do you think they got up there? It's the chemtrails. It's the Illuminati. They did it. No, I mean, again, it's funny. Some of these things are funny, because I used to say for so long, oh yeah, water vapor's heavier. Yeah, because it makes sense, right? It just does, because you feel heavy. But this ain't about how you feel. Facts don't have feelings, as we say. So it is lighter, and that is why we have clouds. And then eventually, when clouds get to a certain point, and it actually gets, they start to clump together, and then we get rain, right? That's what we're seeing. All right, so absolute versus relative humidity. This is one of the most important concepts that you need to understand psychrometrics, okay? Now, I want to be really clear here. There's a way that I explain this that is perfectly functional. Okay, so the way I'm going to explain it is a perfectly functional way of explaining it that is not scientifically accurate, right? So you get some science nerds and they'll talk about all this other stuff that doesn't really mean anything to us. So I'm going to say that air holds water vapor. Air does not actually hold water vapor like a sponge, okay? It comes down to partial pressures. It's a much more complicated thing. But in terms of how we're going to think about it, we're going to talk about air holding water vapor, okay? And here's the way we're going to talk about it. If you have a cup of tea or a cup of coffee and it is cold and you try to stir sugar into it, only so much sugar is going to be absorbed into that cup of coffee or that cup of tea, right? Eventually you'll have the crystals in there. You heat it up, it can hold more sugar, right? Hotter coffee can hold more sugar. Got it? Makes sense? Same thing is true of air. Hotter air, higher temperature air can hold more moisture, right? And when we talk about relative humidity, we're talking about how much moisture there is in the air compared to how much it can hold. That makes sense? I'm going to say it again. How much can it hold and how much is it holding, right? So we use an example. I've got this big old flask of water here. Is this yours? Okay. Shay is very good about hydrating. He's in really good shape, great health, so he uses a big thing. Here, I'm drinking soda because I'm in bad health. Okay, so my cup here represents a lower temperature cubic foot of air. Okay, right now my cup is about 50% full. So I would say it's 50% relative humidity at this temperature. He has much warmer, much higher temperature. It can hold a lot more. If it's 50% full, it's still 50% relative humidity. But which one has more in it? If I were to take his 50% and dump it into mine, it would overfill it, right? Because at each temperature, you only have a proportional amount or a certain amount that it can hold. Does that make sense? So when we say 50% relative humidity, we're not talking about how much total moisture there is. It's how much total moisture there is in relationship to how much it can hold. Okay, I just keep saying it so that you get it. Everybody get it? Everybody get it? Makes sense? Okay. So what that means is you may have a case where the air is very hot and it's at 50% relative humidity and it has a lot more moisture in it than air that is cooler on a cooler day or at night that is 80% relative humidity. Make sense? So that's really, really important. And this comes up a lot when you think about things like attic air. Okay, so attic air, you may go in the attic and be like, well, look, it's only 60% relative humidity up here. But when you start looking at things like dew point temperature or total moisture content, it may not be that high relative humidity, but it has a lot of moisture in it because it's warmer air at a higher relative humidity. So, quick jumping to the end conclusion here, just so you're clear about why I'm doing this. Attic air is no bueno inside the house. When it comes in, it starts raining really quick. As soon as you cool it down, it starts giving up its moisture really quick. All right. As the temperature changes, the relative humidity changes even if the absolute humidity stays the same. Okay, so we're going to use the attic air example. So if I take this cubic foot of attic air that's 120 degrees at 50% relative humidity, and I'm like, oh, 50%, that's not bad. And I take that cube of air and I bring it into the house, all of a sudden it hits 100% relative humidity like that. Even though the amount of actual moisture in it stayed the same because it cooled down. Because cooling it down means that it can't hold as much moisture. It's the same thing. You take the cup of coffee, you put the sugar in it, you let the coffee cool, all of a sudden the crystals show up again, right? Now it can't hold as much sugar again. And that's what's happening. So a lot of people will say, you get water or you get mold where hot meets cold. A lot of people will say that. That's an oversimplification, but often it's workable. Like that does kind of sometimes work out, but really what it is you get moisture when hot, wet air hits a cold surface, a lower temperature surface. And that's why in this room right now, because the RH is pretty high, you get, well, that isn't my cup, you get a lot of sweating on the outside of a cup, right? I mean, that thing's sweating pretty good. If I brought this into a room that was significantly cooler, maybe same relative humidity, but 70 degrees, it wouldn't be sweating nearly as much because there's not as much moisture in the air. Does that make sense? So it's a very basic concept, but it's really, really important to grasp because when you start to pay attention to mold problems in a house, a lot of times we'll start measuring Well, like for example, you were talking about you measure 60% relative humidity in this part of, oh look, it's 60%, that's not too bad. But then you take that same psychrometer and you go up to the peak, up beside where the vents are, up near the attic space, and now it's 75% relative humidity and it's warmer. Okay, that air has a lot more moisture content in it for both reasons, right? It's warmer and it's a higher relative humidity percentage. But even if it was the same, so even if it was down here, 75 degrees, 50% relative humidity, up there, 80 degrees, 75% relative humidity, which one has more moisture in it? Up there, right? Because that's absolute moisture. Absolute moisture generally matters more to us. And again, in a tropical climate like this, it may not be that terribly hot, but it stays pretty warm, and you have really high relative humidity percentage. Like really high. Go ahead.
So, yeah, what you're saying makes a lot of sense. Sometimes we go in and see duct work where, because of the static pressure, trying to release some of it, we cut out ducts inside the attic, and it's pulling all of that humid air right inside the space. So for sure, the humidity is going to go up significantly.
Yeah, big time.
So that's a no-no, right?
No. Yeah, that's a no-no. And it wouldn't matter if it was supply or return. It wouldn't matter unless you were dehumidifying the attic, right? If you had a dehumidifier in the attic and you were specifically controlling the humidity in that space, now it's okay to communicate that space, that air with the rest of the house. And sometimes if you have an isonine, a foamed attic, you may use that strategy, and that's okay. But you really need to be looking at the absolute moisture. So what is the total moisture content of this air? And the way we do that is through dew point. Okay, that's kind of that's the cheat way that we do it. All these crazy lines on this thing, like who the heck uses these things anymore? But you can use calculators. There's psychrometric calculators. Munters makes one that's a really good one if you want to mess with it sometime. There's a couple others out there that are good. But really the ones we care about most often are relative humidity. We care about dry bulb temperature generally. We do care about wet bulb temperature sometimes. That was actually one Willis Carrier started that one. Wet bulb temperature is super cheesy. We'll talk about that. But one of my favorite ones to think about is dew point. It's actually not on this list. Surprising. Oh, there it is. No, it's not. I didn't put it there. And dew point basically tells me this is dew point right here. This scale right there. So when we cross the lines of relative humidity and dry bulb temperature, we can get what our dew point is. Now, if you use any of these sort of psychrometric probes or whatever, you can easily find that. Measure Quick, you can easily find that. It'll give you the dew point temperature, and all that tells you is if something is that temperature inside of that air. So if I have a cup and the dew point temperature is 80 degrees, and that cup is below 80 degrees, it's going to build up dew on it. The air around that cup is going to give up its moisture and it's going to rain. That's basically what's happening with my cup here, is the air that's right beside my cup on this boundary layer, it's achieving that temperature and it's raining right here, localized rain. Does that make sense? And so dew point, when we're dealing with mold, moisture, any of that kind of stuff, is always what we're kind of chasing. And so when you have an air mass in an attic, as they often are, you might have a 90-degree dew point. That literally means if anything is below 90 degrees in constant contact, like if you're blowing air over it, it's much less likely. It kind of has to actually achieve that temperature around it, which is why moving air can sometimes help reduce condensation. It's not like magic. A lot of people think it's like re-evaporating it or something. All that's happening is that when air is still around here, it's able to sit here and the air actually achieves the temperature of the cup. If I'm blowing air over it, then as the air doesn't really have time, it's passing by it so quickly it doesn't have as much time to settle and actually achieve that temperature. Another way of saying dew point is the point at which air is at 100% relative humidity. So when air is 100% relative humidity, that's dew point. A lot of people will say, this is kind of another dumb thing that people think, and I thought in the past, if it's raining outside, I thought that it would be 100% relative humidity outside, right? Because it's raining. Well, but the rain is coming from the clouds. That just means it's 100% relative humidity where the clouds are. In fact, when it's raining often, the raindrops actually condense water on them and actually reduces the relative humidity of the air around you. Once it stops raining and then it warms up again and now the water starts evaporating off the ground, then the humidity jumps way up. But if you do it sometime, if you protect the sensor and you go outside and it's raining, a lot of times you'll notice the relative humidity drops. And this goes back to, a lot of people say Willis Carrier invented air conditioning. Have you heard that before? Willis Carrier invented air conditioning? Does anybody know what Willis Carrier actually invented?
Ice and fun.
What's that? It wasn't really ice, but it was a dehumidifier. And it was a dehumidifier because he was trying to control the relative humidity in a paper factory in New York. Okay, so paper factory, the paper warps if it's not the right relative humidity. And how he did it was he took groundwater, because in New York groundwater is cold, it's like 55 degrees. He took groundwater and he just ran it down like a plate, and he ran air over the water. And that decreased the humidity. And people are like, how on earth does that happen? Well, because that water was cold enough that as air came across it, it was at dew point on the water, and it actually gives up its humidity to that colder surface. It's just like an evaporator coil, but we're just using water as the thing that you're giving up the moisture to. That's all he invented. Compression refrigeration was invented 80 years before by other people. He just came up with the word air conditioning. So it's kind of he was a good marketer, basically, is what it comes down to, and good on him for it. I'm a Carrier dealer today because he was good at marketing and making up words. I've tried that in my marriage, just making up words for things, new things, just to see if I can get away with stuff like, honey, I just called that biggity boo. And she's like, no, that's not okay. I'm like, all right, whatever. Doesn't work. So don't try it. The dew point is the point at which 100% relative humidity is achieved. Does that make sense? That's all. Water molecules are super, super interesting. Like, again, we could talk about water molecules for days. But the thing to know about water molecules is that they are attracted to themselves. They have this two hydrogen atoms, and they have a negative and a positive imbalanced side, and so they like to stick together. And you see that the fact that they create droplets, the surface tension on water, all these weird behaviors that water has on it. But it also means that water is attracted to surfaces. It conducts heat. It has all these different things, and it can really, really ruin ductwork. It can make a big mess of ductwork. And you were talking to me about polyiso and how you guys start to use that. And that's a better product. It's harder to work with, which is the challenge that a lot of people face. But it's a good product because it does prevent some of this. But when we see sweating on ductwork, okay, I just want to hear some of your experiences. Do you see that? First of all, do you see that a lot? Do you see duct sweating? So I'm not talking about, there's a couple different problems that we're going to talk about here. Some is vent sweating in the space, stains on ceilings, that kind of stuff. But right now I want to focus on duct sweating in the attic, okay? When do you see that the worst? What are some of the worst cases where you see duct sweating in an attic? Go ahead.
When the R718 leaks out, with R718 refrigerant leak.
I get it. Water. Okay, I see this guy. He's trying to trick me. Good one.
That's when your temperature, you reach below dew point.
Yeah. Anytime you do get below dew point in the attic, that's when you get duct sweating.
When it's resting on the insulation, a lot of times the sand versus it's hung up.
Yep. Have you guys noticed that where it's sitting on the insulation and underneath there, it'll sweat really bad? What else do you notice about sweating in the attic?
Radiant barrier, well, a lot of sources of moisture all over, but you get rid of bad when you have a radiant barrier, but the place is not, it's still open, so it's not vented properly, but the attic is still open. You got a radiant barrier, and you got a moisture problem. A lot of times it's really bad if you had, a unit, a drain back up, the unit's wet.
Yep.
Right? Now that's dripping water.
Right.
And there's water in the drain pan that's hot, it's got humidity coming from inside, and it can be crazy.
Yep.
Everything's wet.
Yep. Mold crazy. And so he's bringing up a couple things. So go ahead. Were you going to say something?
Yeah, when the attic is really hot.
Attic is really hot. Yep. What's that?
Cool down.
When it cools down?
No.
No, the quality ice, so you're saying.
Oh,
Yeah, material.
the material sweats more?
Yeah.
Okay.
What about like right around the collars?
Yep.
Things that have less insulation on them,
Yep.
fitting or something like that.
Yep. So a couple key things are most likely to make duct sweat, but let's focus on, again, why. So duct sweat when the surface temperature reaches dew point. Anything sweats when the surface temperature reaches dew point, period, of the air around it, right? So how can we solve the problem? Change the dew point of the air around it to make the dew point lower, or change the temperature of the surface so it's higher. That's all we can do, right? That's how you solve any kind of mold or moisture problem. Increase the surface temperature or decrease the dew point of the air, right? So we can, in a lot of cases, we can do both of those things. So let's talk about the surface temperature of ducts in attics. What can we do to increase the surface temperature of ducts? Well, like Matt said, when you're making connections, right, one of the worst things you can do, first off, is to have leaks. If it's leaking air out, well, of course, that's a problem, right? Cold air leaking out is an issue, so don't make joint connections that leak. There's a lot of different ways you can make connections. I have a whole sequence of the best way, the Neil Comparetto way, which is a little extreme. But just make sure you don't have leaks. Liquid applied mastic is one of the best bets. Usually, one of the places people miss most often is where the collar actually attaches to the duct board or to whatever duct you're using, the actual collar. There you go. And that was the next thing I was going to mention. Usually, it's not just coverage, though. It's also compression, right? So what you see a lot of guys do, especially with flex, is they do this. And again, you guys are great here because you can do whatever you want, right? You can get away with whatever's best. A lot of in our market, inspectors just love mastic so much. They just want you to use mastic for everything, and they want to see it all the time. Mastic is for the air barrier, right? The air barrier is the inside of the duct. The insulation and the radiant barrier is the outside of the duct. You really don't want to compress that insulation. If you compress it with the Panduit, if you take tape and wrap it real tight, even a lot of guys will take the insulation and they'll really roll it up, right? They'll roll it up and they'll say, oh, well, that's good insulation. Well, no, the insulation, what makes insulation good insulation is the air, the fluffiness, right? So you want that outer jacket, that radiant barrier, you want that to be attached directly to the silver. You want it to be sealed all the way around, right? That helps keep moisture from getting in. And you want that insulation on the inside to still be fluffy. So even the way we do it at my company, because it's what inspectors require, where we take that duct and we push it up against and we put a strap around it, and then we seal it with mastic, it's not great because that strap that's around the insulation on the outside, it's squeezing it. And when you squeeze that insulation, it tends to sweat right there around that Panduit strap, right there around that band strap. Am I saying words that relate? Do you guys call it Panduits? Is that all this? Okay. So the best way to do that is to do it nice and smooth onto the, so attach that inner liner, make sure it's really well sealed. You can use mastic on that if you want. And then when you pull that around, my favorite way is to actually just attach it with tape on the outside and don't compress that inside insulation at all. If you use silver tape and you pre-clean it with alcohol, you spritz it with alcohol, wipe it down, and then use a squeegee, it'll stick really good. If you want to go real crazy, you can use mastic tape, and that stuff will stick to anything, like Matt was saying. It's a little nuts to work with, though.
One more time. You said things condensate when the air or blown, whatever the humidity is higher.
It's the dew point. Temperature is higher. So the humidity is higher, but dew point is that combination of temperature and RH, relative humidity. Because you may look at the relative humidity and say, well, no, it's 70%, right? But yeah, if the air's 120 degrees at 70% relative humidity, that's still going to be like a 95-degree dew point. So at 95 degrees, if that duct gets to 95 degrees on the outside, it's going to start condensing if there's a 95-degree dew point.
Just one thing. Okay. If you don't connect to the collar to the duct, if you do it properly, even when you use the mastic, say, if you cut the hole properly, not big enough, and you put it there, you let coolers from the side, like he said. Just push the insulation properly, make the hole nice and tight, and push the insulation, then put it the tight strap and seal around like a glue and tape it properly. I guess you don't have problem condensation.
Yeah, and then again, so if what you're saying, yeah, so making sure that inside is completely sealed, that inside is the seal, right? That's also really the mechanical connection, like that inside being mechanically solidly connected. And again, what I typically see is a lot of times people default to really relying on Panduits because they don't do a good job with tape. Because they're like, the tape's not sticking, because they never clean it. Like having a little alcohol spritz, a little wipe it, man, everything sticks great then. Like it really will stick really good. It's when guys aren't using tape squeegees and they're not cleaning it that then the tape has a hard time sticking. Again, I've done it many different ways, and that's my favorite way. The only reason I can't do it that way is because where we are, the inspectors won't pass it because they think it has to have a Panduit strap and it has to have mastic on the outside. But the mastic on the outside doesn't do anything for you. It's on the inside that you care about. That's the air seal. That's the air barrier. Does that make sense? Okay, so that's basic. Don't compress insulation. So like Matt said, where insulation lays on across a truss, where the duct lays across the truss, where it lays across the insulation, there it gets colder, right? Because now it's touching another surface. By keeping it in the air, now it has hot air all the way around it. That hot air actually keeps the surface temperature up. You don't want the outside jacket of that duct to get colder, right? You want the outside jacket of that duct to be more like the temperature of the attic. So kind of an interesting thing, when we went away from the black jacketed ducts to silver ducts, silver flex, everybody sees that now like it's all silver in the attic for you guys, right? Okay. When we did that, we got more sweating problems. And the reason is because the old black jacketed ducts picked up more radiant heat on the surface, right? It got hotter. Now that's not good for efficiency, but it is good for duct sweating, right? Because now the surface was warmer, and remember, what's the key to keep ducts from sweating? One of them is to make the outside warmer of the duct. If the outside is warmer, it's going to sweat less. In fact, you could there's all kinds of crazy things you could do to solve sweating. You can blow hot air on surfaces and all of a sudden sweating will go away, right? I mean, you know this if you're trying to defog a windshield. You see this, it's what you do, right? You can defog it that way. And so it's the same sort of principle. Realistically though, what we need to try to do is keep ducts suspended well, so that way they can be the same temperature all the way around, make sure that we don't have duct leaks and don't compress insulation. Those are the best tips, but you're still gonna get cases where everything starts sweating. And like Simon said, why does that happen sometimes when we have radiant barriers? Why does that happen? Have you ever seen it happen? Except a client has a radiant barrier in a vented attic and everything's sweating like crazy. Have you ever seen that? You know what I'm talking about, radiant barrier. Like they have the shiny stuff underneath the roof deck. You seen that happen? A lot of times they didn't have a problem. Then they had somebody put that in, and then all of a sudden they do have a problem. It's fairly obvious why it happens. Because before when you didn't have the radiant barrier, the ducts were radiating to that ceiling, to that roof surface, and they were getting warmer on the outside, right? That's how radiation works. Radiant heat transfer between the hotter surface and the duct, that was keeping the duct outside warmer. Now when you put the radiant barrier in, that cools down the outside of the ducts. So they start sweating. Everything starts sweating. Because you didn't do anything to remove the moisture from the attic. Right, putting a radiant barrier in doesn't magically remove moisture from the attic. All it does is just cool all the surfaces down. When you cool all the surfaces down, all of a sudden surfaces that were above dew point now are below dew point, and they all start sweating. And people will say, what do you do about that? Well, you tell the client they have two options. Either they can seal their entire attic and dehumidify it, or they can rip the radiant barrier out again, or they can live with mold and all die. You don't say that. No, but it is. It's a really, in our market, we get it all the time. Happens all the time. Because there's companies that go in and they sell it as an upgrade. Oh man, this radiant barrier is going to be amazing. It's going to save all your problems. The next thing is vented attics. If you vent an attic more, oh, go ahead.
We've talked back and forth about this for like 40 years. So, I don't know. Did we all hear that? I just want to make sure we all heard that.
Talk back and forth like what? Like?
About duct sweating, why do they sweat?
Okay.
Because what I've heard what is often said is the attic is too hot. And that's why it's sweating. Right?
Yeah.
Based on what you're saying, it's actually almost the opposite.
Yeah, it depends on how you, so the attic has too much water in it is the reason why it's sweating. And this is where when people are like, hey, you need more ventilation. Okay, here's so radiant barriers are one of the worst things you can do. The other, probably even more worst thing you can do is put a powered attic ventilation fan in. Okay, because then what happens is, yeah, they might sweat a little less in the attic, and now everything in your house starts to sweat. Because now what you've done is you've created another new pressure driver, right? Because your house, no matter how much you try, the inside is still connected to the attic somewhat. right? You have all these, cans and all these ways, gaps and cracks where it's connected to the attic. Now you put a vent fan in the attic, so what happens? You're sucking air and it's coming out of the house. A lot of it is. And now what's happening? Well, it's all coming in the front doors and the windows and everywhere else. All of a sudden, the relative humidity spikes inside your house. The loads go crazy in your house. So it may help reduce at the attic just a little bit because of airflow. Like we talked about, airflow does help reduce sweating a little bit, but it's by a weird way. You're not actually changing dew point. It's just that the air is moving faster past that cooler surface, so it doesn't give it much of a chance to condense. That's basically all it is. So you may see a little less sweating, but now everything in the house is going to become a problem. Does that make sense? So don't power vent attics is a really bad idea. Radiant barriers is a really bad idea in humid climates like ours.
What's our radiant barrier?
A radiant barrier is that like silvery, shiny stuff that they hang under the, yeah.
It's like somebody took a bunch of aluminum foil and just filled the attic.
Yeah, so what is the solution? The solution is seal the attic, dehumidify the attic, okay? You don't have to actually insulate the attic. You can just seal it, right, and dehumidify it. You can't seal it and not dehumidify it because then you still trapped all that moisture in the attic that was in the attic before, right? So that's not really a great solution. Now there are some people who talk about being able to seal it and then like dehumidify it one time and then just like maintain it then with the air conditioner and a couple small little like vents in it. Like I've heard different strategies, but what's much more important is to keep new water from getting in the attic. When you're blowing air through the attic from the outdoors has all kinds of water in the air. All you're doing is introducing more water to your house when you're blowing air into the attic. Does that make sense? Say it again?
Fresh air coming from outside.
Yeah, fresh air coming from outside, again, like so fresh air coming from outside is designed to solve one problem. And that is to keep elevated levels of carbon dioxide and VOCs, volatile organic compounds, from the inside of the home, right? So you have chemicals, you're breathing, all that kind of stuff. That's what fresh air coming in does. But fresh air coming in also brings a bunch of moisture with it. So bringing in fresh air is likely, if you don't do something else, to cause moisture issues in the house. You have to handle that somehow. And there's ways you can do it. Some people will say ERVs, but really, the only really effective way to deal with a lot of moisture is a dehumidifier. Now, I'm not a huge, so to be clear here, I'm not like a big dehumidifier fan. I don't love them. They break and they're another thing you have to work on and they're noisy and they're a pain to install sometimes. And so like I'm not saying that it's a silver bullet that solves all problems, but what I am saying is that in a humid climate, if you want to solve moisture issues, you seal the attic, you dehumidify it, and you have equipment that's set up really good for the house. In fact, if you dehumidify the attic and just dehumidify that, put a small like 70 pint, something like that in the attic and seal it, then you've so much reduced most of the moisture drivers for the house that probably now your air conditioner will do a pretty good job. Like it'll probably solve most of the other issues. We've seen that happen a lot. Like if you're on a budget, that's the way I would do it. Seal your attic, foam it, remove the ceiling level insulation if you can. You don't need to do that, but it is definitely preferred. And then stick a 70 or 98 pint dehumidifier in the attic and just let it go to town and do its thing, right? It's still going to be warm in the attic because dehumidifiers actually do increase the temperature. The discharge air of a dehumidifier is warm, but it's dry air. It's a dry warm, and that's fine, right? Does that make sense? So, is that a easy solution? Is that a solution a lot of people are going to want? A lot of people won't want it, but it's a lot easier than a complicated, like tying it into this or that or all this. And I'm going to show you some of that when we get to the dehum section. Might be tomorrow by the time we get there, but that's really the solution. In the meantime, if you have a vented attic, it's all about how you do your ductwork. Making sure that you don't have leaks, making sure you're not compressing insulation. Now, here's the next thing that I want to show you. So all of this comes from a presentation called condensation. If you really want to understand this, it's on YouTube. It's for free. It's really long. It's kind of boring. But he talks about how this all works. And this guy is the guy who knows how to solve these problems. He lives in Naples, which is even more humid than where I live. They've had all kinds of hurricanes. And he's like, Johnson's AC in Naples is like the company that people go to solve this problem. Very successful at this. And the point of everything that he's showing you is that the temperature of the air inside the duct has almost nothing to do with the temperature of the outside of the air on the outside of the duct. So when people do things like trying to speed up airflow in order to get your supply temperature up so that way they don't sweat, that's a fool's errand. It can slightly decrease duct sweating, but really what affects the temperature of the outside of the duct is the conditions on the outside of the duct. And it stands to reason, right? Like if you warm up the air on the inside just a little bit, that doesn't make much of a difference to what is on the outside. And his argument is also, because in Florida they tried to make R8 insulation standard, so thicker insulation on the ducts. Thicker insulation on the ducts has very little to do. It's like he shows it here. If you change from R6 to R8, it raises the surface temperature by less than 2 degrees Fahrenheit. The outdoor temperature around the duct plus 5 degrees raises surface temperature by 4 degrees. And supply air temperature plus 5 degrees reaches the surface temperature by 1 degree. The point is, the air temperature and the radiation around the duct is what matters much more than the temperature of the air or the insulation of the duct. Does that make sense? So the conditions around the duct, the temperature of the air and the radiant effect around the duct that's keeping that temperature of the duct up matters much more than the temperature of the air inside the duct or the R value of the insulation on the outside of the duct. And this has all been tested, scientifically proven in a humid climate like ours, like yours.
Really, really important to not try to solve the duct sweating issue by ramping up the fan.
There you go.
Right? Because it's done that sometimes. And of course it doesn't work. And then you end up making the house very, very humid. And
right.
Another moisture problem in the space.
Correct.
Right? And then
yeah, and this is where, and so we're going to talk a little bit about sources too here in a minute, but that's the attic part. That's sweating in the attic. So we can't also confuse issues in the attic with issues inside the house, because those are two different problems. Go ahead.
Convince a customer, like how do you persuade him to get the attic sealed? Because around here, adding the extra insulation and the barrier is not exactly cheap.
Sure.
How would you have that conversation?
I would say you're rich, just do it, stop whining. Is that okay? No, I'm kidding. No, again, and that is where once you know how to tell the story, like hey, and so it depends on your client. Like some clients are going to be engineering minded. They're going to need you to prove to them, well, look, we've got all that. That all exists. You just got to put it together, right? Hey, here's the engineering data behind that. This is why. Case studies, white papers, all that stuff. Building Science Corp has done all kinds of stuff on this. Happy to show that to you. Most people don't care about that, though, right? Like that's like 2% of people are going to care about that. Most people just want to know, like, is this going to fix my problem? Yes. Well, what if I just tried this? The other company said if I put in a variable speed air conditioner, that's going to solve all the problems. Well, it won't, right? And that's the truth. It won't. It's not going to solve the problem. So once you're confident on that it's not going to, then you just sell them. I understand a lot of people say that, but it's not true. What's true is if you want to solve that problem, a variable speed air conditioner is great. It's great for comfort. It does help with relative humidity inside a little bit. Load matching, all that. Comfortable year round, that's good. But it's not going to solve that problem, and it's not going to drastically solve your relative humidity problem. Kieran.
Sorry, when you say sealing that, you mean spray foam?
I mean, whatever it takes to get that attic so it does not leak to the outdoors anymore. So that would be your soffits, that would be your roof vents, that would be anything that leaks to the outdoors, sealing it, so that now it's inside the envelope of the building versus being outside of the envelope. Now,
essentially, why I'm asking that is you've got a great rusty dairy on it really well. We've tried this with the things to stop his ducts, all his ducts to swim terribly. He shares the attic space with the neighbor as well. His unit sweats as well. That neighbor keeps it at 80, 85 on 9 most of the time, where Fred keeps it at probably 72. We always thought it was variable speed, running it low and trying to humidify so it's lower temperatures. But ducts are all sweating, so we put a dehumidifier on it, but it didn't help. But I just suddenly thought about something. He's got insulation, like just regular like fiberglass insulation, shut in all the eaves except 1 or 2 little openings to allow a little bit of air circulation. So I'm wondering if
little openings to the outside?
No.
To openings to where?
It's also On the eaves.
He blocked using fiberglass, so they didn't actually seal it. They just used stuck fiberglass.
Like bad insulation?
Oh
yeah, that's not sealed, yeah.
Rated barrier. Nothing sealed.
There's no point in even putting a dehumidifier up there if that's the case. I mean, like, that's just wasted energy, yeah. No, you need to seal it, like where air can't get in and out of it type of seal it. Because you also have air, and water has this other crazy property where it will actually make it through any sort of porous surface. It can actually like work its way through those surfaces, and it moves in the direction of higher dew point to lower dew point. So higher actual grains of moisture to lower grains of moisture through those surfaces. So it will make its way in unless you actually seal it, unless it is no longer porous.
I'll tell you why that one didn't work. The dehumidifier didn't work because I went there the other day. It's because when you put in the dehumidifier, okay, not only is it not sealed, which is bad, but I mean the radiant virus did a pretty good job. It's pretty tight, so you know it's sealed more. It's not perfect, right? But the real problem with the dehumidifier is the supply. It's one supply pumping in right out of the whole house dehumidifier, 90 point. The return was ducted into the living space. So now you're pulling out living room air, which what you should do is pull air from the very top of the attic.
Correct.
Because now you're not pulling in the humid air. To make the dehumidifier the most efficient.
You're doing the opposite of what you should do. Right.
You ruin the performance. Okay?
No, right.
You need to pull it from the top, right, and supply it from far away, you know?
Right. You want to feed that dehumidifier with the most nasty wet air that there is. That's where it's going to do its best work.
We tried to explain that to him.
That's why that did.
If his and Roddy's thing is like, yeah, but then my air handler's going to sweat again. I'm like, no, it's not.
I told it to do all of that.
Yeah. Anyway, so the strategy is, and again, this is the beauty of here, is that you don't have to argue with inspectors too, because with us, we have to argue, like we always have to re-educate inspectors. Here, like look, as long as the attic is sealed, that's the important part. The insulated part isn't really that important unless you have a capacity issue. Insulation is only about capacity. So if you can seal that attic any way you can, it doesn't matter, you could use foam board and caulk or plastic sheeting or whatever you want to use in order to get it so it doesn't leak to the outside anymore, and then dehumidify it, you're going to solve that problem. Full stop. The end. Don't communicate to space air unless there's a reason to do that. Why? Why would you want to be bringing attic air? Because it's still going to be hot air, generally speaking. Why would you want to bring that into the space now? If you get it dry in the attic, though, a lot of that attic moisture is making its way into the space. If you get the attic dried out, then the space is going to be much better too. Does that make sense? The other thing that a lot of people overestimate is the positive or negative pressurization that you can do with things like a dehumidifier. So a lot of people will say, well, yeah, bring in some outside air, put that through the dehumidifier, and then pump that in the space, and that's going to get you under positive pressure. No, it won't. Because you're not going to get a house under consistent positive pressure under most cases, because people have bath fans, they have kitchen exhaust, they have all these other things that they're pumping out of the space. You're generally not going to make that happen, right? Which brings me to my next point, which is if you have houses that have moisture problems on the inside, okay, let's talk about the inside of the house. One of the first things I want you to look at is source control. Where is moisture potentially coming from? And if you have people who are leaving, you know, they have kids and the kids take showers and they leave the bath fan on all day long, right? Well, yeah, that's bringing in fresh air, but it's also bringing in fresh air all day, right? So if it's pumping air out, if you have a 100 CFM bath fan, 100 CFM is coming in all the time. And if they're not home, they're at work, whatever, why? Why do you need to ventilate that way? So things like humidity activated bath fans, for an example. That can really help in a space where that's a significant portion. Because a lot of people are like, well, look, my kids don't take that many showers. That's not the main thing. That's not the main thing. You're right. It's that you're leaving that bath fan on all day long. That's pulling in outdoor air all day long. Just like I said, the issue with leaving the fan in the on position, most people believe that it's the re-evaporation out of the drain pan and off the coil. That's a part of it, but it's only a fraction of the reason why that's a problem. The main reason that leaving the fan in the on position is a problem is because now all day long you have that mechanical driver of pressure that's bringing in outdoor air. And that happens because your ducts are never perfectly sealed. Even in a perfect world, they're not perfectly sealed. Now again, if you seal the attic, now that helps solve the problem, because then even if your ducts do leak, that air and that pressure is staying within the boundary layer, right? It's another way to keep it in. So you have to think about like 1,000 cuts, solving this problem by 1,000 little cuts. Same thing with kitchen exhaust. Some people have these gigantic kitchen exhausts. And if you just educate them and say, hey, how often do you cook? Oh, I cook, like we cook a lot actually. Okay, you have like a 2,000 CFM kitchen exhaust. Just run it on low. Don't run it on high, because it's going to be like, that's a lot that you then have to deal with. And back to what I think you were the one saying this, one of you said this, that like once moisture gets in the stuff in your house, in your couches and in your furniture and in your bedding and in everything, it takes a really long time to get it back out again. So you're always kind of chasing it, which is why even staying on top of something as small as, don't run that gigantic exhaust on full bore unless you need to. Go ahead.
So on the surface, they will have vents to exchange air for the attic. But you're saying
Seal them.
seal.
Yes.
Seal the attic.
As long as you dehumidify it as well. You can't just seal it. You have to seal it and dehumidify it. But what I'm saying is that that's one of the simplest ways to use a dehumidifier is to seal the attic, take a little 70 or a 98 and plunk it in the attic. No ductwork, nothing, wire it up, drain it, done. No interlock with the system, no fancy controls, nothing. Just in the attic, done. So much easier. You don't have to explain anything weird to the owner. You don't have to worry about float switches that connect one to the other because the drains connect. You don't have to worry about any of that. Just get the drain outside somehow, however you do it. Well, you would do it if you're still using the drain for the system, I guess. That would still be a concern. But it's a much simpler strategy.
So no humidity.
It has one built in. It's just yeah, just a simple one. It's super simple install. You can still make good margins on it. And again, is it always going to solve every problem? Well, it depends. Like if you go to a 10,000 square foot house with a gigantic attic with multiple, no, probably not. Like you have to think that through. But it's a very fail-safe install, right? Like it's definitely going to help. And in almost every case, it's going to solve at least the duct sweating issue. And it will certainly help to some degree the indoor space issue. A fan in the attic? To where? Just around in the attic. Sure, that wouldn't hurt. But again, that's the same thing we're talking about. Like it only is really going to help if you're getting significant air velocity over the area that's likely to sweat. So just moving it a little bit is not going to make a huge difference.
And it's definitely not going to solve it everywhere. You're still going to have sweat in some places and you have to hold. It's not fixing your overall.
Right. Go ahead.
What about ERVs?
Okay, so ERV, anybody here know what an ERV is? Energy recovery ventilator. An ERV is an energy recovery ventilator, and what it does is it allows for balanced ventilation. So when you're bringing air in from the outside, you discharge air from the inside, and it helps prevent the house being under positive or negative pressure. And when those air streams exchange, when that wet air comes across, it exchanges some of its moisture to the air that's being released from the house, okay? They don't really work in this market, meaning they will exchange a little bit of moisture, but there's no drain on these ERVs. So you know they're not moving much moisture. The only moisture that's being moved is in vapor form as they have this air exchange across this core. It's window dressing in our market. In markets where they like barely have a moisture issue, sure, right? So like in Portland, yeah, ERVs work great. For a lot of applications. But for here, I wouldn't waste your time. You're not going to get a good result. You're going to charge the customer $2,000 to put one in, and it's going to do essentially nothing for them. They do make, what is the one, Zender? Zender makes a really high-end ERV that does have a drain, and there's some heat pump ERVs that do a little better. But again, for what you're going to spend on it, you're going to spend the same as you would do for a ventilating dehumidifier, or just a regular whole house dehumidifier. It doesn't have to be ventilating in this application. So, what's that? Just do that, right? And this market, that's what we do all the time. And again, a dehumidifier is a pain because you got to put it in place. You can maintenance it, you got to put a filter in it, but you can charge for that, and that needs to be. And that's actually a really good point.
When do you find the high dew point? Day or night?
Oh, hold on. Really good question. When do you find high dew point, day or night? And the answer is that in attics, generally dew point stays fairly stable. Sometimes it'll actually dip down a little bit, but what most people notice is not so much in attics, but in outdoors. A lot of people will say, well, at night it gets dry or whatever. If you ever track relative humidity at night, relative humidity actually will start to spike. And that's just an illustration. And again, this is most places. In a coastal environment, I'm actually not completely sure. I haven't really looked that closely at it. But generally speaking, it actually goes up, and that's because the air got colder, right? So when air gets colder, it can't hold as much moisture. Your actual dew point, it doesn't actually track usually to the hottest, driest days, because generally the days that are the very hottest actually tend to be drier days. It's usually more like kind of damp, wet, but then hot days where it rains and then it like warms back up. Those are generally the times that you get the highest dew point. In an attic though, it actually tends to be the highest when it is really hot in the attic, just because it's that relationship where it is higher relative humidity, it can hold more moisture, so it sort of attracts more moisture. But it doesn't go down as much as you would think, right? And again, the reason why things sweat more at night is because everything cools down at night. So you actually will get more sweating in the attic at night, but that's because, it's not because the dew point is necessarily higher, it's because all the surface temperatures are lower in the attic, if that makes sense. The actual moisture content, it had to go, where would it go, right? It has nowhere to go. Cool, any other questions? I feel like there was something else I missed here. All right.
So for a ventilating dehumidifier, like if we want to introduce fresh air, what's the best strategy to do that eventually?
Well, that is all the way at the end of this, but let's jump to the end. Let's see if I can find it real quick. If you do want to introduce, let's see here. If you do want to introduce outdoor air into the actual space in order to dilute CO2, help with VOCs, that kind of thing, then this is the way to do it. And this is the actual attic version of this diagram. So you bring it in from outdoors. You can bring it through a blower box if you really want to control the level of airflow. Otherwise, that's why it says optional. You can just use a balancing damper. And you bring it into the ventilating part. You have an outdoor motorized damper that you can control, so you can decide when you bring it in or out. And then you put it into the supply duct. This is very, very important. Do not put it into the return duct of an air handler. Okay, because what happens is the dehumidifier pulls all this moisture, and then it's drier, hotter air, and then you dump it into the return of the air conditioner, and then the air conditioner doesn't remove moisture. So you took what is a pretty good dehumidifier. An air conditioner is a good dehumidifier. The only problem with it is it also cools at the same time. So eventually it shuts off, right? It has to. Whereas a dehumidifier, it runs over the evaporator coil, removes the moisture, then runs back over the condenser and heats it up again. So the dehumidifier has the advantage of not only dehumidifying, but also of increasing the runtime of the existing equipment. Now you may say that's not an advantage, that costs more power. Right, it does cost more power, but it's an advantage as far as humidity control. When you take a dehumidifier and you dump it into the supply duct, it does multiple things that are helpful for you. One of the biggest is it actually warms up the inside of the duct as well. Now it's not a massive effect, like we mentioned, but it does actually have some impact, and it does reduce sweating, especially of grills. Right, because now the air coming out of the actual grill is a little bit warmer, and that's going to help keep the grill from sweating. So if you're having issues in the space, this is a good way to do it. Now, it's still not going to bring in a lot of air, outdoor air. You might bring in 100, 120 CFM tops. So it's not going to be that much better than running a bath fan in terms of bringing in outdoor air. It's just going to bring it in a much more controlled way, and you can dehumidify it before you bring it in. The problem with bringing in outdoor air is, where do you put it? Right, like wherever you put it, it's going to want to mold up on you. It's going to want to create moisture on you. How is it controlled? Right. And so this is a controlled way where you're putting the air in a place that it's not going to cause any harm. It's not going to hurt anything. You're putting it into a dehumidifier. Makes sense. But you can very easily overwhelm the dehumidifier with outdoor air too. Like outdoor air has a lot of moisture in it, so like you can easily just sort of negate the value of the dehumidifier. Well, so will it increase the velocity? So this will work regardless if the system is running or not running. So if the system is running, it's going to mix in with the supply air. Now it is going to increase the supply duct static pressure. But these things, when you look at the data on them, they don't run a lot of airflow. They're not like super high airflow devices. So a couple hundred CFM total, up to 300 CFM. So you have to kind of think about that. That is a downside to it. But again, it's powered. But again, you could even interlock it. There's ways that you can design it where you could have it come on only when the system cycles off if you want. I don't generally prefer that, but you can do that. And when the system cycles off, then that's going to be the only air going through the ducts. Now you have to be careful because if that vent is blowing, right, like in someone's bedroom where they're going to feel it, they're going to feel hot air coming out sometimes, and some people get really ticked off about that. So that's why no matter what you do with a dehumidifier, it's going to be a little challenging unless you completely create its own duct system, right? And you know, that's a whole thing. The advantage to this is it does help with the vent sweating and that kind of thing. You are going to reduce vent sweating.
So is it okay if that independent return comes from the attic so that you can accomplish? No.
Mm-mm.
So how would you
You do too.
space and dehumidify the attic?
I would do two. If you don't want to do two, then you can create a system where you do either or intermittently. Tim DeStasio just did a really good case study doing that, where it would do the attic for a while based on a sensor in the attic, and then it would switch and do the
Mechanical dampers.
right.
That can kind of switch it from attic to house.
Yeah. Tim DeStasio, I don't know what's Tim's channel. He just did a whole podcast with me on it. Yeah. Yeah. He just talked about it on my podcast like 3 episodes ago or something. And it's not that complicated. It's just it's always going to be a trade-off. Can you take a little bit from the attic and put a little bit in the attic from it as well as do the house? Sure, you can. But like attic air is always like not my favorite to mix with the house anyway. You know, it's like just not. It's still attic air, like rodents, other stuff. Like I don't know. Like even when you foam an attic, I don't love communicating foamed attic air because it does tend to off gas. Like there is sometimes an odor, which is another thing. My favorite way of sealing an attic is closed cell foam, not open cell foam, closed cell foam, especially in a hurricane market, because now you're tying together the whole, and that's actually kind of not a bad way to sell it, honestly, because I have it in my house. It's great. It's sound dampening. But it also like really ties together everything. Like that whole roof system is now completely connected and stable. It hardens, and it also doesn't off gas as much, so it's not as stinky. But anyway, it depends on your client, obviously, whether or not those are, you know, again, there's all kinds of ways you can do it. If you are going to tie it into your equipment, though, I'm just telling you, this is the only way to do it. You're going to be tempted to put it into the return, but you might as well not do it then, because you're going to take your air conditioner and make it into a bad dehumidifier because you're putting dry air right into the bottom of your air conditioner. Does that make sense? You don't want to take dry air and put it right in the bottom of your air conditioner that's designed to remove moisture. That ruins the benefit. So I much prefer either doing it independently or going into the supply.
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community. For techs, by techs.